In this video, we're going to practice some hybridization. So I'll draw some big, messy organic molecules and we'll indicate the hybridization on the atoms. We can practice some formal charge also. And then we're going to get into drawing orbital bonding pictures. So first of all, I'm just going to draw some organic molecules here. So just kind of bear with me as I make stuff up. Drawing organic molecules is actually pretty fun because you just have to remember to never have more than 4 bonds on carbon, never more than 4 bonds on hydrogen, more than 1 bond on hydrogen. Don't break the octet rule on oxygen or nitrogen either, and then you can just pretty much connect stuff however you want. So our first one here, do know if there are lone pairs, I am going to show them for this exercise. So if there aren't lone pairs shown, then there aren't lone pairs. So the first thing we're going to do is go through and look at formal charge. So we're going to use that line, which are representing our bonds, and then dot method, right? So my very left carbon, I don't have any lone pairs on it, and I have 3 bonds. So my number of valence electrons for carbon is 4, right? And then if I look, I have 1, 2, 3. So 4 minus 3 is a positive 1. So there's a positive 1 charge. Oops, I want my eraser. There's a positive 1 charge on that carbon. If we look at the carbon in the middle, I guess this only works if I have a different color here. 1, 2, 3, 4. So 4 minus 4 is 0, so no charge on that. Oxygen, it's 6 valence electrons. 1, 2, 3, 4, 5, 6. 6 minus 6 is 0, so no charge on that. Got a little crazy with the undo. And then hydrogens, 1, they all have 1 bond, so no charge. So this would be the formal charge on this molecule. To determine hybridization then, I'm just going to look at each atom and I'm going to see how many electron groups it has. Remember, if I have 4 electron groups or electron domains, it's going to be sp3. If I have 3 electron groups or electron domains, sp2. If I have 2 electron groups, it's going to be sp. And remember, a single bond, a double bond, a triple bond, and a lone pair all count as 1 group each. So this carbon here, I have 2 electron groups, right? I have that double bond and I have that single bond. So my hybridization on that is going to be sp because I have 2 groups. This middle carbon, I have 3 electron groups, right? A double bond and 2 single bonds, so sp2. This one, my oxygen, I have 4 electron groups, 2 single bonds, and 2 lone pairs, so sp3. Right, hydrogens can never be hybridized. Why is that? Yeah, right? Hydrogens only have s orbitals. Right? Hybridized orbitals are combinations of orbitals and there's nothing to combine it with, right? All I have is an s orbital. I can't combine it with anything else because there's nothing, right? Just an s. So hydrogen cannot be hybridized for that reason. So you can just always ignore those when doing hybridization. So let's do another. Let's do a ring, which is kind of annoying to draw. Next week we'll actually learn kind of a shortcut way to draw organic molecules, but for now. Kind of running out of room there. Okay. So if you need to pause the video to copy that down, by all means do so. So formal charge first. I'm just gonna let you guys do this one on your own, and then I'll come back and put the formal charge on it. So again, if you want to pause, go for it. Do it yourself, and then start it when you're ready. Okay, so hopefully you guys gave that a shot. And the only one that I actually have charge on is this carbon right here. It has a -1 charge. That carbon has 3 bonds and a lone pair. So if we're doing the counting bonds in lone pair method, right, lines and dots, 1, 2, 3, 4, 5. So 4 minus 5 is a -1. So that has that charge. Everything else looks okay unless I missed something. I'm giving it a double check here, but all my carbons seem to have 4 bonds. Yeah, it looks good. Okay, hybridization. So really, you just look at all the atoms except for hydrogen, because again, hydrogen, you can't be combining it with other orbitals when you only have one orbital, so they're not hybridized. So the carbon, I just put the arrow on. It has 2 electron groups, so sp. And actually, this is another one. You guys, it would be a good idea to just pause the video and try it on your own. You really just have to count. As long as you know what to count, and then remember this up here, it's pretty straightforward. So if you want to pause it, that would be wonderful. And then just start it again when you're done, and then you can check your answers before I go any further. So this carbon, sp. This carbon has 3 electron groups, the 2 single bonds and a double bond, so sp2. This one, sp3. Oxygen, it has a double bond and 2 lone pairs, so that's 3 electron groups, so sp2. This is gonna get kind of messy here. This carbon has 2 single bonds and a double bond, so 3 electron groups, so sp2. This one, it has 4 single bonds. This one has 4 single bonds. Nitrogen, it has 3 single bonds and a lone pair, so still 4 groups, so sp3. This carbon, sp3 also, same reason as nitrogen, right? 3 single bonds and a lone pair. And then this carbon, sp2. So hopefully you guys did pretty good on that. The ones that tend to be a little confusing, if you struggled with oxygen here, that totally makes sense when you're learning. But again, remember, a single bond, a double bond, a triple bond, and a lone pair, right, non-bonding pair, all count as one group. So that has a double bond and then 2 lone pairs, so 3 groups. 3 groups is sp2. Let's do one more. So let's look at carbon, a bond to carbon. Let's do another nitrogen. This time, let's put 2 hydrogens. Actually, let's just have 1 hydrogen this time. 1 hydrogen, and we'll do 2 lone pairs. Doing very good at drawing geometry on this one. This carbon that I just drew there, that I put the 2 hydrogens and the oxygen on, would be tetrahedral. And I don't know, that'll work. So formal charge again first. Please give the video a pause and do it on your own. And then when you're ready, come back and check your answers. So hopefully you guys did that. I'm going to start on the left and kind of go over. So carbon here, I have 3 bonds, right? A double bond and a single bond, but I'm going to count that as 3. So 1, 2, 3. And then the 2 lone electrons, 4, 5. So 4 minus 5 gives me a -1 charge on that carbon. The next carbon only has 3, right? It has a double bond and a single bond. I don't have any lone pairs or any hydrogens on it, so 4 minus 3 is a +1. The carbon, this one right here, that one does not have a charge, 4 minus 4. My nitrogen actually has a -1 charge, right? Nitrogen is 5 for its number of valence electrons, and I have 1, 2, 3, 4, 5, 6. So 5 minus 6 is that -1. This carbon right here doesn't have a charge. And then my oxygen has a -1 charge. This is actually a pretty ugly molecule that wouldn't probably exist very happily, but we didn't break any valence rules and we did our charges correctly, so we're okay with it for examples. Hybridization, again, please try this on your own to give the video a pause, and then when you're ready, come back and check your answers. So this one here, I have 3 electron groups, so sp2. This one I only have 2 electron groups, so sp, sp3, 4 electron groups, 4 electron groups, 4 electron groups. This one's pretty boring. 4 electron groups, sp3. So how'd you guys do? I'm hoping you're getting it. If not, please post something in discussion or we can talk about it on the video conference this week. But this is something that I hope that you can be pretty good at if you're not already. We will be using it a lot this semester. So the next part is going to be what we call orbital. Oop, that's not an R. Orbital bonding pictures. And I don't know if this is like the official name for it, it's what I call it. But what we're going to do is we're going to essentially draw these molecules, but we know that bonds aren't aligned, right? We know according to valence bond theory, we're actually overlapping orbitals, and those electrons are found in that region. So that's what we're going to do. For all of our bonds, we're actually going to draw the orbitals, overlap them, and show how those electrons are born or shared. So let me erase this. And we'll start with a pretty straightforward one. We can actually start with our just tetrahedral carbon here, just methane. I shouldn't say that. If I was to put different groups on here, they're also tetrahedral. So carbon, we go back up to this. These are all tetrahedral, right? That has 4 electron groups. This has 4 electron groups. And they're not methane, but we're just going to start with carbon bonded to 4 hydrogen. So first thing I would do is determine hybridization like we just did, because you don't know what type of orbitals to draw if you don't know what the hybridization is. So this is sp3, it has 4 electron groups, and then my hydrogens are always going to just be s orbitals, right, unhybridized. So we need to know what these things look like if we're going to draw them. So remember our s orbitals are spherical, so we'll just draw a circle. Our p orbitals are dumbbell shaped. Remember, if something is sp2 hybridized, it does have an unhybridized p orbital, so we are going to draw that. Right? If we go back up to this guy here is sp2 hybridized, so there is an unhybridized p orbital on there that we would draw. We are going to draw all our orbitals. And then sp, like hybridized orbitals, are literally combinations, and what they look like are combinations. And I'm going to do my best to draw these, but I'm not a very good artist. So an sp3 orbital is 3 parts dumbbell to 1 part sphere. So it's still dumbbell shaped. It still has 2 lobes like a p orbital does, but they're a little bit rounder than a p orbital would be, and then the 2 halves are a little mismatched. And that's probably closer to an sp2. I'm going to redraw that, try to make it a little nicer. So let's actually, sorry guys, I'm going to exaggerate this one a little bit so you can kind of see the difference. So I'm going to make those 2 lobes a little bit longer. So it's going to be a little bit fatter, and then the 2 lobes are going to be a little mismatched. An sp2 now is 1 part S for every 2 parts P, so it becomes even more P-like, so even a little bit more rounder and a little bit more mismatched. So this is supposed to be fatter than that. That is that. Like I said, I'm not very great at drawing them. When we draw our orbital bonding pictures, I'm not looking for perfection as far as being able to differentiate between sp2, sp3, and then sp, which is 50% sphere and 50% dumbbell. So it becomes even rounder, and then its other lobe becomes even smaller. So this is even the fattest. So as we go from here to here, it becomes more S-like, right? This is 50% S, 50% P. This is 1/3 S, and then this is 1/4 S. When we draw our orbital pictures for these, I am only going to draw one of the lobes. So this bottom, the smaller lobe, I'm not going to draw those in my picture. You can if you want, but it gets messy, and I do have to be able to grade it. So unless you're really good at art and you can make it look beautiful, please don't include those other lobes. For p orbitals, we are going to include both. So carbon, let's do this picture here. I'm usually going to put the atomic symbol for the atoms, not for hydrogen, but for like carbon, nitrogen, oxygen, in the center where the nucleus would be. So again, if we go back to these, this is where my nucleus would be, in the center here. That's actually kind of big. It doesn't overlap into the lobes. It's actually, oops. Remember that it's a node, so it's a region with no electron density, so it's like right there. I don't know if you can even see that color, sorry guys. It's like right there in the middle, right? It's that space that I'm not putting anything in. So I'm actually going to make it bigger, and I'm going to put the atomic symbol there. So basically this, I'm going to put a carbon. And then it's sp3 hybridized. I know if something is sp3 hybridized, I have 4 sp3 orbitals. So I'm going to draw those. I know that it's arranged tetrahedrally, so I'm going to draw those in a tetrahedral arrangement. So if I want an orbital coming out at us, we're going to kind of shade it a little bit. And then if I want an orbital going back, we're going to dash it. And again, I'm not drawing this part. It's there, but I'm not drawing it. And then I know my s orbitals are spheres. Make sure you overlap them. One of the big mistakes I see is people will do this. They're not bonded then, right? Remember valence bond theory, we have to actually overlap those orbitals. So make sure you overlap them. And that would be my orbital bonding picture for this one. You can put the electrons in if you want, but it's hard to see and gets pretty small. So I'm just going to assume that if you're overlapping those orbitals, that you know there's electrons in there. So let's actually, I said this and it was at the end of the last video, but let's do this again because we're going to need it. So if it's sp3, remember that's 4 electron groups. We did that in this video, but there's going to be 4 sp3 orbitals. If it's sp2, that's 3 electron groups. There's going to be 3 sp2 orbitals and 1 p orbital, right? Unhybridized or traditional. If something is sp orbital hybridized, there's going to be 2 sp orbitals and 2 p orbitals that are unhybridized. So you do need to have all of those, right? So this was 4 electron groups. This was 3 electron groups. And this was 2 electron groups. Before we do another example, I want to talk about pi and sigma bonds real quickly. These also should be terms that you know from 151. I know it's been a while, which is why we want to make sure we review them here. So a sigma bond, we can use the Greek letter sigma to represent it, is formed from the direct overlap of orbitals. So direct overlap. If we were to draw a line connecting the nuclei of the two atoms in the bond, that line is going to pass right through that overlapping region. So the internuclear plane. So again, if you were to connect the two nuclei, so internuclear, goes through the overlapping region. So if I was to draw just my two hydrogen atoms, right, so diatomic hydrogen again, and I have a nucleus in here and a nucleus here, and if I was to connect those two nuclei, right, that line just went right through where it's overlapping. So that would be a sigma bond. If we go up to this example, remember this carbon is where my nucleus is. Here's my hydrogen. So right through the overlapping region, through the overlapping region, through the overlapping region, and again through the overlapping region. So those would all be considered sigma bonds. We want to label those. Those are all sigma. A single bond will always be a sigma bond. And after we talk about pi, I will make a little list to say that, but single bonds are always going to be sigma. The other type of bond that we can have are pi bonds. And pi bonds are the sideways overlap of orbitals. If you were to connect the two nuclei with a line, it does not go through the overlapping region. So the internuclear plane does not go through the overlapping region. And an example, we'll use p orbitals here. If I was to take two p orbitals and overlap them this way, remember my nuclei are in the center here where this node is. So if I was to connect them, they do not go through these areas here where they're overlapping, right? They're overlapping here and here. So this would be an example of a pi bond. We can have sigma bonds with p orbitals also, right? If we were to have, let's do it up here, if I was to overlap my p orbital, sorry, that's kind of messy. More my eraser. If I was to take my p orbitals and overlap them end to end like this, again, my nuclei are in the center here. If I was to connect those, it does go through that overlapping region. So we can have sigma bonds with p orbitals, but if we overlap them sideways like we did down here, it's going to be a pi bond. So a single bond is always going to be a sigma bond. A double bond, and we're going to draw some of these, is going to be a sigma bond and a pi bond, so one of each. And then a triple bond is going to be a sigma bond and two pi bonds. So let's do another example here. Let's do this guy. We've used this as our example a few times this semester already. This is formaldehyde, by the way, if anyone cares. So we're going to draw our orbital bonding picture, and then we're going to indicate sigma and pi bonds. So we're going to add to this. First thing is I do want the hybridization. Remember, hydrogens can't be hybridized because I only have an s orbital. There's nothing to combine it with. This carbon has 3 electron groups, so sp2. This oxygen has 3 electron groups, so sp2. So carbon, remember if it's sp2 hybridized, we'll scroll all the way back up to here. I have 3 sp2 orbitals and then a p orbital also to get on my picture. So my 3 sp2 orbitals, they should be all the same size roughly. My oxygen, it's also sp2, so 3 sp2 orbitals. I'm going to put my hydrogens on here. These two have lone pairs in them. And then I'm missing my p orbital. So I have a p orbital in each. And I'm not very good at drawing the perspective on this. If you guys are really artsy, by all means do it. But the p orbital is actually perpendicular to the plane of our sp2 orbitals. Remember, they're trigonal planar. They're just in 2 dimensions with bond angles of 120 degrees. A little bit different for the oxygen because of those lone pairs. But the p orbital then is going to be perpendicular to that plane. So if my sp2 orbitals are completely flat in your screen, nothing coming out, nothing going back, then the p orbital, one lobe is sticking out at you and the other lobe is going back behind. I don't know how to draw that, so I just put it on there, but do know that it's perpendicular. Your best attempt at doing it, if you want to do it right, is to maybe wedge part of it and then dash the other part. Remember, wedges imply that it's coming out and dashes mean it's going back behind. So that's probably going to be the best way to draw it. I want to try to make that neater, but it is perpendicular. So we're going to have a p orbital on here, and that's coming out at us. And then this part is going back behind, right? 2 lobes. And then this carbon also has a p orbital on it, and that's coming out. And then they're actually overlapping sideways to form that double bond. Because they're spaced out, remember our p orbitals, if I wanted to put it in the same perspective, they would be overlapping right like that. They'd be overlapping here and here. I can't really draw that because I have them spaced out because of that sigma bond between the oxygen and the carbon. So the way that we're going to overlap them is we're just going to connect them like this. So those guys are overlapping sideways. The book does have some pretty good pictures. I'm sure you can find some better ones on the internet too. So by all means, try to find a better picture. But this is, I'm drawing it for you instead of showing you a photo because you have to be able to draw it also. So to get a more realistic version of it, by all means, look one up. But I want you to kind of work through this with me. So this is a pi bond. Do not label, I'm going to do it, but then I'm going to cross it out. Don't do this because it's not 2 pi bonds. You now have 2 pi bonds. The blue is 1 bond, right? If I go up to my picture here, they're overlapping in 2 spots for 1 bond. So a pi bond is going to overlap in 2 spots per bond. So don't do that. And then this is a sigma. This is also sigma, and then this one here is also sigma. So I have a double bond here, right? It's made up of 1 sigma and 1 pi bond, right? 1 sigma and 1 pi bond. So let's do another example. Let's have carbon, hydrogen, let's do a triple bond. Another carbon, and then we'll put a nitrogen on here. So same thing, we want to go through, figure out the hybridization, so when we draw it, we know what we're doing. So this is going to be sp, sp, sp3, and then sp3. Remember the sp hybridized ones, let's go back up. These guys are going to have two, not eraser, highlighter. These guys are going to have two sp orbitals and two p orbitals. So I'm going to start with the sp3 hybridized carbon. Remember, sp3 is tetrahedral, so I do want to try to draw a tetrahedral, right? I'm going to have two in the plane. I'm going to have one coming out and one going back. I'm going to try to draw it so it mimics the way that I draw the Lewis structure. So I am going to try to draw it where the two that are in the plane are going to be these two, and then I'm going to have a hydrogen coming out and a hydrogen going back. But instead of using lines, I'm going to use my orbitals. So I get that we're not all really good artists, but I do expect that you make a reasonable attempt at trying to draw the geometry. If you just drew it with 90-degree bond angles, I am going to take off points for that. You do need to try to make it tetrahedral. I can do better. I want you to do your best. So I will try also, and that was not my best attempt, so now you get to watch me do it over. Well, that wasn't much better, but that's kind of what I got. What you cannot do is do not do this, right? If you give me 90-degree bond angles, I'm going to put a big old red X right through it, right? And I'm not going to take points off. So please try to make it tetrahedral to the best of your abilities. You can do better than the one I just put the X through. I know you can. You can go either way now. I'm going to put the nitrogen on next, but again, you can do this in any order you want. That is also going to be tetrahedral. So do your best again. Your best is not making it 90 degrees. I know you guys got more in you than that. As you're painfully watching me do this, you know that sometimes you have to erase it a few times before you get it right. So one of those orbitals has a lone pair in. It doesn't matter which one. I'm going to, again, try to mimic the picture I drew, and then I have hydrogens on the other two. Let's get our hydrogens on here before we forget them. Now I have my sp hybridized carbon. So that is linear. Remember, if it's sp, we have two electron groups, two of those sp orbitals. That's bonded to another one, which is also going to be linear. So you want to make sure that these are going to be 180 degrees, and then we'll throw that hydrogen on there. What we're missing, remember, if it's sp hybridized, I do have two p orbitals on each of those carbons. So I'm going to draw one on each first in the same color, and then we'll go back with a different color. And they are perpendicular to each other, so I'm just going to kind of slant them a little bit. So I have a p orbital here, and then those guys are going to overlap to form a pi bond. And then let's use green. I'm going to draw these offset the other way to show that they're perpendicular. And then they're going to overlap to form another pi bond. Remember, if I have a triple bond, I have one sigma and one pi. So labeling our bonds, this is a pi bond, pi, sorry, sigma, 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 and sigma. And then I have two pi bonds, the green one and the pink one.